Nuclear reactions. A nuclear reaction takes place when a nucleus, or a particle, collides with another nucleus and a change occurs in the nature of that nucleus. For example, we have here a helium nucleus striking a nitrogen nucleus. Then on the other side you wind up with oxygen and a hydrogen nucleus, or a proton. Now, in nuclear reactions, electrical charge, nucleon number, mass energy, linear momentum, and angular momentum are all conserved in the reaction. These can take place spontaneously, for example, in the sun. The sun is constantly putting hydrogens together to get helium, and then putting heliums together to get higher mass elements. Or they can occur in laboratories, in physics labs, where we bombard elements with neutrons or protons or other elements and see what happens. And we do this to find out what is the structure of the nucleus. On the previous slide, we showed one specific example of a nuclear reaction. Here's the general format for any nuclear reaction that occurs. We have a bombarding particle A, which could be as small as a proton or as large as a carbon nucleus or even a lead nucleus, but that's the particle that's being accelerated. It strikes another nucleus, and then out of it you have a recoil here, which is now a different particle from either one of these, and another nucleus. So to some degree these two letters could be interchangeable, but what we're interested in studying is what happens to the X nucleus and what nucleus comes out of it, Y, the major nucleus. Another way to write that is the original target struck by this particle A, particle B comes out, and we're left with nucleus Y. Let's define a reaction energy, or Q value. Okay, Q value is the energy available from the difference in mass of the reactants and the products. For example, the mass here can either be less than the total mass here or greater than. And depending on whether it's less than or greater will tell you whether it's releasing energy or it's taking energy in. So we define the Q value as the mass of A plus the mass of X, so those are the two particles on the left side, minus the mass of B and the mass of Y, which are the two particles on the right side. We multiply it by c squared, so it's an energy. And another way of showing this is the mass defect in atomic mass units times 931.5 MeV per atomic mass unit. And this will then give us the Q value in energy. It'll give it to us in MeV. And just one more point, the mass defect is the mass, it's just this term right here. Okay, it's the original masses we started with minus the masses we finished up with, and the difference in those masses is energy. Since mass energy is conserved, Q is equal to the change in kinetic energy. Now, if Q is positive, and remember Q is the mass defect, which is the mass of the reactants minus the mass of the products. If Q is positive, the products will have more kinetic energy, so energy will be released in the reaction. This reaction is exothermic, and more energy is released than is put into the reaction. If Q is negative, the reactants have more kinetic energy, which means energy is absorbed in the reaction. This gives you an endothermic reaction, and more energy is put into the reaction than is released. So that's not a very good way to generate energy if you were looking for an energy source, because you're putting more energy in than you're getting out. Threshold energy is the minimum energy necessary for the reaction to occur. So let's work some problems. Find out if this reaction is exothermic or endothermic. So if we come up with a Q value that's positive, it will be exothermic. A negative Q, it will be endothermic. So first we have to find the missing component. We have hydrogen of mass 2, which is called deuterium, that's an isotope of hydrogen, strikes nitrogen, gives you an isotope of helium that only has one neutron. And what's this here? Well, we have 1 plus 7 is 8. Over here we have an atomic number of 2, so we need a 6 down here. Up here we have a total mass of 16, This is 3, so we need a 13. So that turns out to be carbon. We could find the 13 and 6 by math, then we'd have to look at a periodic table to see which element has an atomic number of 6, or you could just remember that that's carbon. Now we're going to find the mass defect. We take the atomic mass units of the reactants over here, and notice we take them out to many decimal places because that's what we need in these types of problems, because even small numbers make big differences. And we have, here's the mass of deuterium in atomic mass units, here's nitrogen, then we subtract away the atomic mass units of the products. So here's helium, and here is carbon. We do the math, and we get a negative 0.002207 atomic mass units. We now find the Q value, or the reaction energy, by just E is equal to the mass defect times the speed of light squared. We convert the mass units to kilograms using this conversion factor. We then have the speed of light. Normally we use 3 times 10 to the 8th meters per second, but because of the significant figures here, we take it out to 4 decimal places. We square it, and then we find that Q, the reaction energy, is minus 3.294 times 10 to the minus 13th joules. Now, since that's a negative Q, a negative reaction energy, it is an endothermic reaction. More energy has to be put into this than comes out at the end. Neutrons are very effective in nuclear reactions, and the main reason is right here. They have no charge, so they are not repelled by the nucleus. Had Rutherford done his gold foil experiment with neutrons, which of course they hadn't realized that neutrons existed at that time, but that's all right, the neutron would not have bounced off the nucleus. It would have been hard to find the nucleus because a neutron could have gone right into the nucleus and been absorbed by it. So what we have here is physicists have been able to create your elements with greater atomic numbers than uranium, and these are only created in the lab. They do not exist naturally on the Earth by neutron bombardment. So what we have at the top, we shoot neutrons at uranium-238. Notice again I don't mention the 92 because if you have 92 protons, you're uranium. You get uranium-239. That neutron just goes right into the uranium nucleus. However, that is not stable. It has too many neutrons. So what it will do, it decays and it turns a neutron into a proton. It emits an electron or beta decay and the antineutrino. And neptunium still isn't stable. So that comes down to here. So let me draw the arrow. So you can see uranium-239 goes there. It's not stable. It decays to neptunium. Neptunium is not stable, so that now will decay and emit a beta particle and an antineutrino. You get a whole chain of decays, and that's what nuclear physicists spend a lot of time doing. They start one reaction, then they see everything that comes out of all the subsequent reactions and analyze what happened to the various nuclei. Calculate the reaction energy of the following reaction. Uranium-235 decaying into thorium-231 plus helium. Calculate the mass defect by determining the difference in mass between the uranium-235 and the two products thorium and helium over here. So it's going to be this mass minus thorium and minus helium. So that's what we have right here. Here's the AMU for uranium, the atomic mass. Here's thorium, notice the negative sign, and here's helium. We get a positive mass defect. Now we convert that mass in AMU to MeV per c squared and then multiply by c squared to get the reaction energy. So here's our 0.005027 AMU here times 931.5 MeV over c squared, and we get 4.683 MeV. That's our reaction energy.